It's not videoing.
Now it's videoing. Okay, yeah, I can see the blinking light. No, what I did is the technique I'm about to show you is one of those that the first time, for many people, it feels really strange. After you do it a few times, it becomes not really that difficult. But to help you get through the homework, I have recorded, this will be the 8th example from the homework. So if you need to, you can go to the videos and get extra help, okay? So lots of different problems on the website to help you with this. Pulling out the 75, that was pretty straightforward. Raise your hand if you knew that was what we were going to do. Point, okay? 2 for Abby. Next step, looking for hands. Suppose Carrie?
Would you do like multiply the x into the 5x minus 3?
Look up, please. Look up. Hey, 3 points for Carrie. There's a reason why you can't. He knows why. So the thought is a good thought, and there will be problems in the future, Carrie, where that's what you want to do. You just can't on this one. So why not, Darby?
Because the 5x minus 3 is cubed set to the power of negative 5, so that x squared just set to the power of negative.
This exponent, in short, this exponent makes it so I cannot multiply that through. I'd have to do the exponent first. How many knew it? 0.2 for Darby. So you cannot multiply that out, although in the future, simpler versions you will, but not this complex of a problem. So other suggestions? Please.
Right. 75 antiderivative 5x cubed minus 3 to the negative fifth plus 75 antiderivative x squared redundant dx plus 75 antiderivative x squared.
Okay, look up. I couldn't quite tell because there's a lot to say. You did a good job. Are you saying just to split them into 2?
Yeah, with 75 on both sides.
Oh, gotcha. This is the factor.
Yeah.
3 points for Dave. Look up. London, look up. Okay, please notice with a antiderivative, you can split the antiderivative if things are being added, but not if multiplied or dividing. So we can't do that.
Is there some way that we could anti-differentiate the 5x cubed minus 3 to the power of negative 5 and just kind of forget that the x squared is there for a little bit, and then after we're done with that, deal with it? But
Now listen close. 4 points for Darby. Take 5. Here's why. Look up. Here's why I gave her 5. Her comment is really helpful because many, many people want to do that. It's really common, but you can't. Like it doesn't work. The rules only apply if it's an exact match. So as you look down the rule sheet, do you see any of the 10 rules that look exactly like that? You don't. Shake your head. London.
Could you do like so split the 5x cubed minus 3, and then the 5x cubed times x squared and negative 3, no?
No. 2 points, no.
if there's not a rule for this, does that mean that we're done?
Good comment. Look up.
That would be awesome.
Great. No solutions.
That is the fiction.
You're right, you never go back. You never go back. Hey, so the subject of how to find an antiderivative is somewhat lengthy. Most of the techniques for finding antiderivatives are taught in Calc 2, not Calc 1, which is what we are in. Okay. So for our class, all we learn is some simple techniques which we've already practiced a bit using the formulas. We learn once in a while an algebra trick, like Carrie's idea of distributing. That will come up later in a future homework. And then we learn one more method. So you only learn 3 methods. That's it. One of those 3 has to work. They're not going to give you a problem where one of those 3 methods won't work. So the 3rd method is not obvious at all. And we're about to learn that method now. But I had you go through that little exercise because it does help for you to kind of say, what about this, what about that? And I can just point out, yeah, those are all dead ends. They don't help. When you see two, kind of back to what Dave noticed, when you see two functions being multiplied, now we will see in the future that one of those two functions can be a constant. That is uncommon, but it can happen. More common is two functions. So here we are. Here's one function. Here's another. When you see that, your first choice should be distribution, probably, if it's easy. Otherwise, we're going to do what's called antidifferentiation using substitution.
Okay.
Catchy name, huh? My calculus teacher just called it U substitution, so that's what I use. That's what I'll refer to it as, U substitution. Yeah, here we go, look. U sub kind, U sub smart, U sub important. Yeah, I'll explain that in a minute.
I love that movie. Is that
Somebody, Mikhail Dahl and Eli Lysenko made that last year. So here's how U substitution works. The first thing is what Darby did. You have to recognize whether you can do a U substitution or not, because it doesn't work on every problem. If you try to do a U substitution in a place where it doesn't work, you'll get stuck. So first identify the two multiplying functions. So you need help with that. Next thing, you have to recognize that those two functions are of specific forms. And you're looking for one of 5 different forms. The forms you're looking for are on the pink sheet. They're the rules. One form is this: something raised to a power. So something to a number. Another form that is not on this problem, that it will show up in the future, is this one. 1 over something. Another form you'll see, e to the something. And then the last two, sine or cosine of something. Right again. Come on. So as you look at the first of the two multiplying functions, raise your hand. What form does this have? Come on, it's not hard. What's the form of the first one, Mason? Something to a power. Who knew it? Point. Okay, 2 for Mason. Listen to the words. They're very important. You've got to keep straight the word something versus the word function. You've got to keep those straight. I'm going to use those back and forth, but they have different meanings. This is the first of the two multiplying functions, but the something is just the 5x cubed minus 3. You need me to say that again. So we've got two multiplying functions. You have to pick out the form. You can't recognize the form, you're stuck. So that's of the form something to a number. Therefore, the something is 5x cubed minus 3. Okay? The reason for the sign is this. We're doing a U substitution. That means we're going to take something here, pull it away, and put in its place U. So we have to define what U is. This is where the grammar gets really exciting in this class. We must define what U is. Okay.
Oh, I get it.
U is kind, U is smart, U is important. This is a really good movie, by the way. If you've not seen that, it's a really good movie. But, hey, if you remember the movie, it helps. Not funny. Since the movie is called The Help.
Hey!
Just listen to this. Hey, one more time, watch. You have two, listen to how it connects to the movie. It really does help. You've got two multiplying functions, right? We identify the form, something to a number. The U is always the something. So U is always something. U is smart, U is kind, U is something. Okay, told you it'd help, kind of. Okay, questions? Please.
Does it matter if we read that off to the side or if we just read it kind be written down. So no matter if we wrote it underneath the 75.
Hold on. Ticket question for Dave.
Yeah, Dave.
Look, here's why he's getting a ticket. Look, U substitution is a reasonably complex procedure, and because of that, I demand that you use the notation I'm using. So you do the notation as you see it, otherwise I will not help you. It's too hard. You'll never get partial credit on a test because it's too hard to grade. Like, just follow my notation. Okay. Good question. All right. There's another multiplying function here. That means the other function has a something as well. Please raise your hand and tell me, what is the something of this function? There are two multiplying functions. You must be able to identify the something of each. You figure out the something by looking at the form of the function. Okay? So what's the something in this case? Just x, because this is x to the 2. So it's something to a number. The something is just x. Who knew it? Point 2 for Tegan. That means, back to the movie, U is always something. Something special.
Oh, it makes sense now. U equals two different things.
You cannot, the grammar here is just awesome. You cannot be two different things at once. Okay? Listen.
It's just fun, so do it.
Hey, so only one of the two values is valid, one is not valid. In this case, it's easy. It's easy. You is not valid. You ain't valid neither. Okay. Okay. In this, you're okay. It's going to change from problem to problem, but in this particular problem, it's easy to recognize. We are going to make a U substitution. If you come over here, and everywhere you see an X, you put U in place, you haven't accomplished anything. It just looks different, but nothing's changed. So this will never be a good choice.
Much smarter.
So we're good now. Okay. Please.
So if you have an equation that had like the two functions and you ended up being the same thing for both of them, wouldn't that not happen because you like try to like divide by terms and then just the exponent would change?
We will see. We won't worry about it today because we just got to get started a little bit slower. But we will see a problem in the future where that happens, and I'll help you. Okay, look up. Look up. Next step. We make our substitution. So on the next line we write, this is the same as 75 antiderivative u to the negative 5 power multiplied by x squared multiplied by dx. Okay, keep in mind, this is where we are solving the problem. This is where we are figuring out what are we going to use as substitutes. Please.
So I'm still confused on how the substitution functions you're using as a substitute.
Gotcha. It's okay that we have two of them, right? Are you okay that we identify the something in each,
Yeah.
and that u is always the something? We eliminated that possibility just because it isn't useful.
Why is it?
Because if I come over here and everywhere I see an x, I plug in a u, I'll have exactly the same thing.
Oh, it'll just be different variables.
Yeah, just a different variable.
Okay.
Does that answer your question? 2 points. It's confusing the first time. I totally admit.
Sorry, just so you like.
Oh yeah.
I don't understand actually.
All right.
Are you saying U is confusing?
Yeah, and you ain't valid neither. Okay.
You ain't.
Look. Quiet again. Quiet. Okay. There's nothing on the rule sheet that looks like this either. Keep in mind the goal. The goal is to get something that's on the rule sheet, because you cannot find an antiderivative without using these rules. There's no way. You have to go to the rules. The biggest problem here is you've got a mix. You have some u, some x. The goal here is to start with a complicated expression using x, get a simpler expression only using u. So we want to replace the x squared and the dx. Okay? So you come over here and figure out how to do it. I have this equation that tells me how u is related to x. I got to figure out how dx is related to du. That's what I need. So to do that, I'm going to take the derivative of both sides of this. Questions? The y is not clear yet, so that one just be a little patient. Just 1 minute.
Squared?
The y is funny. Look, yeah, it's not clear why we would do this. It becomes more clear in a couple of steps. Say, look, what you must feel good about is it's legal. I'm not making a guess here. I have two equations that are equal. If I take the derivative of both sides of the equation, it's still equal. Cannot violate equality. This side I can't really do much, so I just write down what I have, which is du over dx. Okay, please remember, the first time we introduced this symbol, look up. The first time we introduced this symbol, we emphasized that this is division. We don't think of it as division all the time because we just pack the symbol around with us. But it's division, it's a slope. It's rise over run. It's rise divided by run. Change in output divided by change in input. That's what derivative is. Everybody good? This is division. This side, you use the green rule sheet. You end up with 15x squared. Thank you. Perfect. Okay? We are trying to figure out something that can be plugged in place of x squared dx. I look at that and go, oh, we've got it. Not yet, but if we just algebrate a little bit.
That's a word?
I invented it. I like it a lot.
Not to algebra.
You have to get.
Say it.
You have to get like what x squared equals in terms of u.
Essentially, think of it this way, Darby. No, look.
It's hard.
No, look at me. Look at me. Look. There's an easy way to think of it. I want to replace all of this. So I want something to say x squared dx equals. How can I get this to say x squared dx equals?
Dx on the other side and 15 on the other side.
Yes, so how do I get the dx on that side?
Multiply by
Yeah. Multiplication.
It's just division. Multiply it over.
U over 15 equals x squared dx.
There you go.
Wait. Yeah.
You should be.
It's just division, so multiply it across. Then move to 15.
But,
So then you just put in,
du,
then you put du over 15.
for all the things?
No, not all the things. For x squared dx.
So yeah.
All the things would be a bit much, but you know.
Well, yeah.
Times. Oh!
Now you have u in all the things.
Yes, which was the goal.
Ah!
Because
It's making sense now.
Okay, pause.
Oh!
Okay, the goal has been accomplished. We started with an antiderivative problem that was complex involving x. We have an extremely simple antiderivative problem that uses u instead. Question? The 15 is a multiplying constant.
So 75 over 15.
And it's a math class, so of course the division works out perfect. Unlike the real world, but whatever. Please.
for the actual AP test, once you take it one step further, if it's the written section, you can just leave it after you take it one step further, right? Because you have U defined.
Oh, no, because the goal of the problem is, so good question, look up. The question is specifically, like, you have to read the symbols. The symbols say, find the antiderivative of this expression using the variable x. So we change to U so we can accomplish the task, but then we're going to change it back.
Okay.
So pretty much you go until the integral sign disappears, or until you use it.
You got to use the integral sign, and then you got to get back to x. Okay? So look here. Look. This now has a rule. Power rule.
That makes sense.
You were. Oh my God.
Capital C or a lowercase c?
No, I don't. It's a good question.
How come we're literally allowed to
That's what
Okay, that makes sense. It makes a
No, because in any problem, like even if you're working a problem where x could have represented something else as well, the rule basically just says as long as you can get the formula to look like this, the rule applies. And then you can
Why
switch that.
only when it looks like that? Because even though it looks
Wow.
like that, it's the exact same problem.
That's the part where I have to confess. I've never gotten a good answer for that.
They just won't, it just
I know it works, I know it's valid, but I can't answer what you're asking. I totally get the question totally. Apologies.
what was that?
You guys can talk later, but anyway, Darby.
Is it okay if you have 5 over -4 multiplied by the rest, or do you have to?
Either way, either way.
Then don't say it like this.
You're good. Tate?
Do you have to put the 5x cubed minus 3 back in?
Yes.
Yes.
Now, there's an exception. Look up. We will soon learn a process that's awfully similar to this that will be slightly different. So just be aware that there's going to be some differences. But this problem wants the answer in terms of x, so you have to. If you don't, you lose a point. So.
Please, Jake, did you do this for the original derivation?
We never did this exactly, but let me say something that maybe you're noticing. Hey, listen. U substitution is the chain rule in reverse.
Okay, I remember doing it.
So we never actually did this, but maybe it felt like it.
Yeah, I got
Hey, look up. In a previous class, they do a U substitution for a different reason. That might be why it's feeling like it. I'm not sure.
Yeah,
Look up.
we did use it.
Different reason. Okay, look up. Look. There's something else you need to notice. Look. Okay, you need to be aware that as you're doing the process, when you get to here, right? Like, look right here. There's a little test you must perform. And if the test fails, you've either made a mistake or U substitution won't work. So there's no sense continuing. We have two multiplying functions. Pay attention to the words function versus something. We identify the two functions. We identify the something from each function, right? This something came from the first function. Therefore, for the process to work, the derivative of this something, right here, this derivative must be exactly the same, except for the multiplying coefficient, as the other function. And it is. This multiplying coefficient is 1 or 75. If you put it back in, it doesn't really matter. This multiplying coefficient is 15. Okay? But x squared is x squared. If that match doesn't occur, you've got something wrong. It's because it's the chain rule backwards. Look at me. When you take the derivative of this, you end up taking the derivative of the something. The derivative of the something is 15x squared. That's where that came from. Remember, this is the derivative of this. Okay, I'll say it again. You have two multiplying functions. You're going to find the something from each. I took the something from the first function, therefore the derivative of my something must be the other function. We'll practice again. Write down, yeah, 8's good. Write down number 8. Go. Write down number 8.
Is this one also